9.5 Example 6 continued. So in this video, we're going to talk about more series to continue from the last video on how to determine convergence and intervals of convergence. So we have this nice little series right here, sigma 0 to infinity, 10x to the n divided by n factorial. Now my gut is saying this is going to converge because n factorial grows faster than a power. Okay, so let's go ahead and use that ratio test. And using the ratio test, I get the limit as n goes to infinity, absolute value of 10x to the n plus 1 divided by n plus 1 factorial times, now instead of writing it as dividing, I'm just going to multiply right away by the reciprocal, 10x to the n. Then I'm going to go ahead and clean that up, so it's the limit as n goes to infinity, 10x to the n times 10x divided by n plus 1 n factorial times n factorial over 10x to the n. Now I can reduce off my terms, so I reduce off the 10x to the n and the n factorials, and that leaves me with the limit as n goes to infinity, absolute value 10x divided by n plus 1. Now x is not dependent on the limit. So when I take the limit, I just have an n plus 1 in the denominator, so that whole thing is going to go to 0. And 0 is always less than 1. So we have that the series converges absolutely for all x, since 0 was less than 1. If I wanted to write this as an interval, it'd be negative infinity is less than x, which is less than infinity. And if it asked for the radius, it would be none. Because there is no radius, because it converges everywhere. Okay, so now we're going to go ahead and look at this second series, which says the sigma from 0 to infinity, n factorial x plus 1 to the n. And if you were to write out each term, that's what they would look like. So now we're going to go ahead and use that ratio test. So I do the limit as n goes to infinity, absolute value a sub n plus 1 divided by a sub n. So this is the limit as n goes to infinity of n plus 1 factorial x plus 1 to the n plus 1 divided by n factorial x plus 1 to the n. So now I'm just going to go ahead and clean that up a little bit. This is the limit as n goes to infinity, n plus 1, n factorial, x plus 1 to the n, x plus 1, all divided by n factorial, x plus 1 to the n. Now I can start reducing things off, and I'm left with, this is the limit as n goes to infinity of the absolute value of n plus 1 times x plus 1. Now n is in the numerator because there's no fraction, which means this goes to infinity, which every single time is greater than 1. So that means that this series should diverge. So there is something that we do need to take into consideration. When we write this is the limit as n goes to infinity of n plus 1 times x plus 1, there is something we do need to consider. We can break this up into two pieces. And the first piece is when x does not equal negative 1. Sure, this thing goes to infinity. I completely agree. However, when x is equal to negative 1, this will go to 0, because when you multiply n plus 1 times 0, you get 0, and you do that before you take the limit. This is that special case that I was talking about, where it will only converge at one particular x value. So we get that the series only converges at x equals 0 and nowhere else. Alright, so we're going to look at this last series right here, which is series from 1 to infinity, x minus 3 to the n divided by 2n. So again, we're going to implement that ratio test. So it's the limit as n goes to infinity, and then it's going to be x minus 3 to the n plus 1 divided by 2 times n plus 1. Times, and then I write this original but taking the reciprocal, So now the next thing I do is I clean that up a little bit. N goes to infinity. X minus 3 to the n, x minus 3, 2n plus 2, times 2n over x minus 3 to the n. So then my x minus 3 to the n's are going to cancel. And I get this is the limit as n goes to infinity of x minus 3 times 2n over 2n plus 2. So I can bring that x minus 3 out with absolute value bars. Times the limit as n goes to infinity of 2n over 2n plus 2. Using an n behavior model, this is going to go to 1. So I'm left with the absolute value of x minus 3 is less than 1. So if I want to find the interval of convergence, I go -1 is less than x minus 3 is less than 1. So then I add 3 to both sides, and I'm going to get 2 is less than x, which is less than 4. Cool, so that's my interval. But before I'm done, I have to do one more step, which is to test the endpoints. So we're going to go ahead and test x equals 2. And the way I do that is I plug that into my original series for x. So n equals 1 to infinity. And then where I saw an x, I'm going to go ahead and put that 2 over 2n. And this is going to give me sigma n equals 1 to infinity, -1 to the n over 2n. So I'm going to go ahead and say this converges, because if I was going to use the alternate series test on this, I would ignore this part and it would be 1 over 2n. And when I take the limit as n goes to infinity, I get 0. So by the alternate series test, that will converge. The next one I'm going to go ahead and test is x equals 4. So this is sigma n equals 1 to infinity, 4 minus 3 to the n over 2n, which is sigma n equals 1 to infinity, 1 over 2n, which I can rewrite as 1/2 sigma n equals 1 to infinity, 1 over n. And I know that this is going to diverge because it's harmonic. So just looking at these, this one is good and this one is not. So then my new interval of convergence is 2 to 4, where 2 is included and 4 is not.